Both Pierre and I have the misfortune of not being able to coordinate our talks with any of the lecturers in this school. So Pierre discussed optomechanics, and I'm going to talk about mostly Rydbergs. In this case, Rydberg molecules. Now, Professor Juni yesterday introduced you to the 4 U's of atomic physics: the ultra fast, ultra cold, ultra precise. Huh?
You're like Governor Perry. What's the thing?
And there was ultra precise, and there was a 4th ultra. Does anybody remember? Ultra stable. Yeah, thank you. So today I'm going to add to it an ultra exotic as being another ultra perhaps in atomic physics. So what I will describe are these sort of so-called ultra long-range molecules, which must necessarily be ultra cold, Rydberg molecules, which have some interesting properties. And in order to introduce you to this topic, I need to also first, I think I will be the only one who will speak about Rydberg atoms or molecules in this school. Just to give you a brief introduction, there is a special issue which came out only a few months ago. I was one of the co-editors in the Journal of Physics B, and which has a list of publications by some of the better known people in the Rydberg field. So if you're interested, you could refer to this. There was another review article which we wrote on ultra-cold Rydberg atoms in very strong magnetic fields, but that's a very sort of a specialized topic. Now, what's the Rydberg appeal? I will introduce you to some of the properties of the Rydberg systems, but it's a sort of a bridge between mesoscopic, the classical world, and a macroscopic, which is the quantum world. It has, Rydberg systems have very exaggerated sizes. You'll see some of the numbers. They have extremely large time scales, and they're scalable, so they're very, for instance, suitable for doing cavity QED type measurements, precision measurements, and also they're extreme sensitive probes of their environment. And because I'm at the Center for Astrophysics, I must always add this, that the first atom which was created in the universe was a Rydberg atom. It was not a ground state. So cold Rydberg gases, in this context, then sort of connect to chemistry, some of which our Roman friends yesterday described, to soft condensed matter. By soft here, I mean really frozen gases of Rydberg system, ultra cold plasmas, and now are being sort of used for information processing, quantum information processing.
Hossein, can I ask you a question?
Sure.
Are there any known cosmological consequences of the fact that when the universe went transparent, that it went that way first through Rydberg atoms?
Yes, the anisotropies in this CMB are the consequences. Yes, because of the fact that you had to really go through the cascade of the Rydberg transitions, and the photons got smaller and smaller as they went through the transitions. So this is the picture of Johannes Rydberg, and this is his handwriting, which when he wrote with the transitions between two different N1, I suppose this is N1 and N2 states, and C1 and C2s are the quantum defects, which I will introduce to you in a few minutes. So this is the Rydberg constant. It's one of the most accurately known constants we know. And these are the sort of the scaling properties, the exaggerated scaling properties of Rydberg systems. The size scales as n squared. So anything Rydberg would typically scale as n being the principal quantum number squared. The time scale for Rydberg system scales as n cubed, Kepler time. The polarizability would scale as n to the 7. And the van der Waals coefficient C6, the long-range interaction between neutrals, would scale as n to the 11th. So for instance, a hydrogen atom in n equal to 100 would be about half a micron in size. It's approaching macroscopic scale, or at least mesoscopic. These are some of the time scales, and the energies are typically in gigahertz. So I'll give you some examples. The largest atom ever observed, for instance, is a Rydberg atom not in the lab, however, but in a supernova remnant, Cas A, which is about 3.4 kiloparsec away from us. The transition which was observed was from n equal to 1009 to, there was a delta transition to n equal to 1005 with an energy of about, 26 megahertz, which translates to a wavelength of about 10 meters. And the size of this atom is roughly about 21 micron. And these are the sort of a superposition of several different images. The outer ones come from infrared imaging. The inner ones is from Hubble, and the inside, these bluish purple, are from X-ray Chandra imaging.
So if that's the largest ever observed, what's the largest created in a lab?
I think in the lab, people have created wave packets of Rydbergs up to n equal to 1200, something like this. I think Barry Dunning has done that. I may not have the latest information, but that's about it. But those are sort of wave packets of Rydberg atoms, many different end states. Now, as I mentioned, Rydberg atoms are now very much in vogue for the fact that they can be used due to this particular property, the so-called dipole blockade, or Rydberg blockade. The idea is that if you excite one atom into Rydberg states, and in its vicinity, if you try to excite another atom with the same laser to the same excited Rydberg state, due to the interaction between these two Rydberg atoms, which can be either van der Waals, C6 over R to the 6, or dipole, D squared over R to the cube, dipole, hence the name dipolar blockade, then this other excited state will go out of resonance. Therefore, it will not be excited. So then in a sort of a blob, in this ultra-cold gas, for instance, where the reds are the ground state atoms, you would only create one Rydberg state, one Rydberg atom, the so-called superatom. And this has been observed. This, I think, is from the measurement of Weider-Mueller, where they have, as a function of time, they sort of monitored the refraction of Rydberg excitation, and they saw it saturate with different intensities. So they saw that you could do the blockade of the system. So, and one of the ideas that we could sort of entertain is this, that you could take, for instance, this blob of the superatom with one Rydberg atom excited, and then make a linear superposition of it and create an entangled system, a very macroscopically entangled system, because you would not know where this Rydberg atom is in this whole ensemble. And just recently, or recently meaning 2 years ago, January 2009, the Wisconsin group of Tad Walker and Mark Safran were able to actually observe Rydberg blockade between two atoms. Now this was in a gas of atoms. This is doing it deterministically between two Rydberg atoms. So one of which was in this dipole trap, a single atom, another one in this dipole trap, separated by about 10 microns, and they were able to see Rabi flopping of the ground state atom as they changed the excitation. Now, in ultra-cold plasmas, these are plasmas which are created in magneto-optical traps. You can also form Rydberg atoms. So if you have a gas of ground state particles in a moth, and this is the harmonic trap for it, the typical densities and typical temperatures, then you bring a shiny laser with it to photoionize it now. This is not to excite, but just to photoionize the electrons out of the system. Then the electrons, which are this red hue, tends to the electrons tend to go away. As they move away, they suddenly remember that their parents have been left behind. The ions are back in the moth due to the space charge, because there's plenty of positive charges behind. These electrons tend to come back. They go back and they come in, and they form these two-component ultracold plasmas in a moth. Now, the ion temperatures are the temperatures of roughly of the constituent atomic ground state atoms. So the temperatures could be millikelvins, microkelvins, tens of 100 microkelvins, but the electron temperatures would be high, in the order of Kelvin. Now, in this process, then the electrons and the ions can sometimes recombine and form Rydberg atoms. And this has been observed in the experiments at NIST of Steve Ralston and company and other, and Tom Killian. They have observed formation, a spontaneous formation of Rydberg states in magneto-optical traps, in these ultracold plasmas. Rydberg atoms also form when you try to form anti-hydrogen. This is from an experiment done at Harvard, Jerry Gabriel's group, where the antiprotons come in this direction, the positrons come in here. Of course, there's a homogeneous magnetic field of about 5 Tesla in order to separate it from ordinary matter. And then there are these segments of electric fields which provide this nested penny trap. So the antiprotons sit here, and positrons, which are oppositely charged, sit in this minimum, and then they heat it with an RF so that the antiprotons and the positrons can get together and form antihydrogens. These antihydrogens, in a very strong magnetic field at about 4 Kelvin, are in Rydberg states. So now, the effort in this field is to bring these antihydrogen Rydberg states to the ground state so that they can be compared with ordinary hydrogen so that, for tests of CPT, charge parity, time invariance. And just very recently, Rydberg atoms were actually trapped in an optical lattice in a group of Diogreto in Michigan. So this is a moth, and with the moth laser, the 5s, 5p transition, this is in rubidium, then the excited Rydberg, not quite Rydberg, but the 5p atoms in an optical potential, because of the negative polarizability of the 5p, sit on the maximum of the optical lattice. And then they turn this lattice around quickly so that the Rydberg atoms go into the minimum and sit in the bottom of the optical lattice. And they have, I think they have demonstrated efficiency of about 90% for the population of the Rydberg atoms in optical lattices. These are typical lasers. Now, before I go on further, I should tell you that not all Rydberg atoms are created equal. And this is to sort of introduce you to the idea of quantum defect. So this is the spectrum of sodium atom. So these are all the s electrons in n equal to 5, 6, 7, 8. These are all the p electrons, 5, 6, 7, 8, d, and so on. And this is the hydrogen atom. These are Rydberg states now. I'm not showing you the ground state. This is the 4 n equal 4 in hydrogen, n equal 5, 6, 7, 8. If you compare n equal to 5 in hydrogen with n equal to 5s in sodium, you can see that they are energetically very different from one another. There's a large difference in energy. Likewise, if you compare n equal to 5p in sodium with 5 n equal to hydrogen, you'll see a difference, and so on. However, if you compare the n equal to 5d or 5f, 5g in sodium with n equal to 5 in hydrogen, you'll see that they're almost degenerate. This is the idea of the quantum defect. Due to the fact that the sodium has a core, it influences the energetics of the s electrons more than it does the p electrons and the d electrons and so on. So the angular momentum provides the centrifugal barrier which pushes away and the effect of the core. So higher angular momentum states would look hydrogenic. This matters a lot in the spectroscopy of Rydberg systems. And instead of going through this, I think I will just pass through it because I want to get to what is more important. But in any way, this is the energy level of an electron in a one electron Rydberg system. Our favorite one electron Rydberg atoms are alkali metals: sodium, iridium, potassium. So n is the principal quantum number, and the quantum defect which then determines the energy level of these systems. So if you take, for instance, the sodium levels, and you look at the wave function for a hydrogen atom, it looks like this. If you were to actually plot the same, in the same n, wave function for a sodium wave function, the electron in the sodium, then it would look like it sort of would be shifted in, and this difference in oscillation of the wave function in hydrogen and sodium is what determines the quantum defect. This term here. Now, I mentioned that Rydberg atoms are sensitive detectors of their environment. Quite a long time ago, of course, in the 30s, Amaldi and Segre decided to put potassium Rydberg atoms in rare gas, okay? Helium, argon, and neon. And what they were expecting was that due to the fact that the Rydberg electron would interact with a rare gas. Okay? So if you take a charged particle and a neutral atom, the interaction is due to polarizability. The electron, the charged particle, polarizes the neutral atom. Therefore, there is a 1 over r to the 4th polarizability, or polarization potential, which is always attractive in the ground state. Meaning, I don't know whether I have it. Yeah. So this would be this. The electron polarizes the ground state atom, and this polarizability is alpha over to the r to the 4th, and it's always attractive. So you would expect the Rydberg lines to be red shifted or blue shifted. Question for the class. If the attraction is positive, if the interaction is attractive. Blue.
It's coming towards
It would
coming towards each other, right? There's an attraction.
If there is an attraction, you would expect the attraction to bring the energy level down, right? Meaning that it would have to be redshifted. Now, for argon, they saw that. They saw that the energy shift was redshifted. However, for helium and neon, the energy shift was blue, to the blue, not to the red. This was explained by Fermi, it's sort of this Fermi pseudopotential. What he said was this, that if there is a species-dependent scattering, or in this case, the scattering length, if the energies are low. I'm assuming, actually, from the lectures of Professor from Professor Pu, that the scattering length is minus the tangent of phase shift divided by k. Okay? In the limit where the k, the momentum goes to 0. What Fermi assumed was that this interaction between the electron and the Rydberg, the ground state atom, then behaved as a delta function, hence the Fermi pseudopotential, where r is this distance, the distance from the core to the electron, capital R, the distance between the two centers of the atom and the two atoms. So that it would behave like a delta function, and the coefficient, the strength of this interaction, would be proportional to the scattering length. This is the Fermi pseudopotential. Which then, if you were to calculate for a Rydberg wave function psi of r, take the expectation value of this potential, you get energy levels which would be proportional to a, the scattering length, times the wave function squared, times 2 pi h bar squared over n. Those of you who worked with the nonlinear Schrodinger equation would immediately recognize this as the nonlinear term in the Gross-Potievsky equation. Except for a factor of 2, this is exactly the same form which appears in the nonlinear Schrodinger equation, describing the mean field interaction in atomic gases. So, therefore, because of the fact that the scattering length between the potassium Rydberg electron and argon and helium and neon, in the case of argon, it turns out to be negative, so it's redshifted. When A is negative, this interaction would be negative. And because the interaction of the Rydberg electron with helium and neon turns out the scattering lengths are positive, therefore you get a blue shift. Okay. Oh. The scattering length, as I said, it's related to the tangent of the phase shift taken at the limit where the momentum k goes to 0. Now, in electron with rubidium 5s, this is the S wave interaction, phase shift. This is the P wave at the different J levels, J equals 1, J equals 0, and J equals 2. So this is the P wave, and it shows the resonance behavior, and this is the S wave. Now, if you take this and extrapolate this S wave phase shift and extrapolate it down to 0, you get to the Wigner limit, which Professor Krem yesterday mentioned, and from which you can extract the scattering. So what we did was to say that in ultra-cold gases, this is the same form of the energy which I showed you a couple of slides ago. This is the scattering length. In this case, it's energy dependent, but that's besides the point here. This is the energy level of the hydrogenic state. And this is for instance, this is an example of a rubidium, in this case 30D, interacting with the rubidium 5s ground state. The Born-Oppenheimer potentials would oscillate as a function of distance between the two atoms. And in the outer turning points, you would have the deepest potential, and they would support bound states. They would support vibrational bound states. In collision, in interaction between the rubidium 5s and the rubidium 30D. It turns out that in rubidium, in the singlet sigma G molecular symmetry, the scattering length is positive, and the triplet sigma U, the scattering length is negative. Just to show you that this is not a figment of imagination, these are ab initio quantum chemistry calculations of lithium-helium potentials. This, as a function of R, this is energy. This is in the case of a Rydberg, lithium in the Rydberg state of 5s, and this is the lithium in the Rydberg state 5p. Then you see that they actually oscillate. These oscillations are due to the fact that the Rydberg wave function is oscillating. So the oscillation of the Rydberg wave function is now mapped into the internuclear distance, the distance between the ground state atom and the Rydberg atom. So it gets mapped into this, and that is sort of manifest in an oscillation in the potential. And these are vibrational energy levels. Separations are in the order of 100 or so megahertz, easily resolvable. This is just to show you the effect of the quantum defect in rubidium. If rubidium, for instance, takes rubidium 35S, so rubidium 35P would be separated from it by about 276 gigahertz. And rubidium 35D would be 57 gigahertz away. And then 35F, another 275 gigahertz. And after that, roughly, all the other angular momentum states sort of come together in a sort of a degenerate manifold. Now, in the S-wave collision, showed you in the non-degenerate case, the collision between the interaction between the 5s and the 30G, you get these potential wells. If now you're in the degenerate manifolds, you have to sum over all the angular momentum states. Here is only D, here is over all the angular momentum states, and if you do so, you get again a set of potential curves which look similar to this. In other words, the oscillations are there because these are Rydberg. If you sort of zoom in this area, you'll see that they can actually also support vibrational waves. Now, if you look at the electron density at this position, for instance, of this non-degenerate manifold, you see a spherically symmetric wave function, a spherically symmetric charge density. And if you zoom here, look at the charge density of the electron, what you will see is a fairly exotic wave function of charge density. This dot represents the core rubidium ion, and the electron which is attached to this core is here, and underneath it is the other rubidium atom, which is in the ground state. So the electron of this Rydberg atom wants to spend most of its time on top of the ground state atom, therefore giving rise to a very large permanent dipole moment. These we call trilobite molecules because sort of the charge density resembles the trilobite fossils, if you're familiar with those. Okay, this was in the S wave. If you go beyond the S wave, this is the S wave interaction between the ground state atom and the Rydberg atom. If you go beyond the S wave, so where you have P wave phase shifts, then the form of the interaction, this is S, and this would be P. Instead of having a form with a wave function, I didn't write it down, wave function squared, here you would have not wave function squared, but the derivative of the two wave functions multiplied. And this is the tangent of delta of the P wave. This 1 stands for P, L equal to 1 angular momentum of the electron. These you had seen before, and this is now, these would be the potentials due to the P-wave interaction. Because of the fact that there is a phase shift, it gets mapped into the internuclear distance, and it shows us the sort of a wave, set of potentials which sort of suddenly drop all the way down, and again, all of these also support bound states. Now, this particular version of the Rydberg molecules were recently observed in photoassociation experiments of the Tilden Klaus group in Stuttgart. So what they did was essentially a very standard two-photon absorption scheme where they went from 5s to 5p, to the blue, and then from there to the red of Rydberg states in n equals 35 and higher. So this would be a spectrum for like n equals 35, spectrum for n equals 36, and 37. And in these peaks here, there are the atomic lines. This is the peak of the n equals 35 rubidium atom, peak of the atomic absorption line. So n equals 36 and n equals 37, separated by their Zeeman levels because of the fact that there is a magnetic field, and the s electron would want to split into plus 1/2 and minus 1/2. However, to the red of the atomic lines, to the left, they saw bumps like this, which are blown up from this box over here. And you can see that there is a v equal to 0, which is identifiable, of the molecular vibrational line, v equal to 1, v equal to 0, v equal to 1, v equal to 0, v equal to 1, in different manifolds of the Rydberg states. So they were able to observe these molecules. And then what they did was, which was very, very interesting, it's sort of an example that you can actually do controlled chemistry, is that with the rotary echo technique, they were able to make the molecules, take two atoms, photoassociate them, make these molecules, and then dissociate them, and on and on and on, in a very coherent fashion. So, and to do that, what they did was to bring in the pulse, run it up to some time, tau p, and then reverse it, the minus Rabi frequency, from tau p to tau. So instead of showing you every one of them, let's just say we take this green one. So they make the molecules at tau equal to 0, and then they send through this pulse through time tau p, and then so that they can dissociate these molecules and bring them down to the ground state. Dissociate them into atoms, and then reverse the pulse and bring them back into molecules. So this is one of the few examples of a reversible reaction of a pure molecular constituents, albeit this is done in a Rydberg system. So there's a time scale, in this case, time scale of the Rydberg system, few microseconds. So, now, what they also did was to subject these molecules to electric fields. Now, the electric fields are in the order of a few volts per centimeters as a function of the relative frequency. So the 0 here would be atomic line of the 35s. So this would be the Stark manifold of the grounds of the 35s Rydberg atom. And it shows a quadratic behavior. In other words, it scales as f squared, f being the electric field. This is the spectra, the Stark spectra for the v equal to 0 of the molecular line. And it also shows a quadratic behavior. So, based on that, they concluded that these molecules were, because they were spherically symmetric, they're S-wave molecules, they only had an induced dipole, or in other words, they had polarizability. So this alpha m is the polarizability of this molecule here. Before I go further, I don't want to go into this. Let me run you through very basic quantum mechanics here. So if you take, because this will help us, or at least help me, understand the process. So if you start with a hydrogen atom, you put in an electric field. Perturbation theory, non-degenerate perturbation theory would tell us that in the ground state, there should be no shift of the atomic line. The reason being that you start with a spherical wave function here, spherical wave function here. Z, your dipole operator, is odd, therefore this matrix element is 0. But you can now take this and generalize it to the fact that the systems in non-degenerate states cannot have permanent electric dipole moments because of the parity and time reversal, which I just mentioned. This is true for molecular systems too. So if they have a non-degenerate states, let's say you take a homonuclear molecule, H2, right? The 2 identical hydrogen atoms. In the ground state is non-degenerate. Therefore, it should not have a permanent dipole moment, and it doesn't. Now, you look at the second order perturbation theory, then you will immediately see that a shift proportional to F squared, being the electric field, develops. So for hydrogen atom, this is just working through what happens in hydrogen system. You'll see that in essentially freshman quantum mechanics, that the dipole polarizability the polarizability of the atom, which is proportional to 1 over F. In the case of hydrogen atoms, 4.5. We know this exactly. But more importantly is that this shift is proportional to F squared. It's an induced dipole. Therefore, H2, for instance, in the electric field would show a quadratic shift. And these are, for instance, because it's a homonuclear molecule. These molecules are also homonuclear. They're made of a ground state rubidium atom and a Rydberg rubidium atom. Therefore, their Stark manifold would also show F squared behavior, the quadratic shift. So there would be a polarizability. So we say that when the ground state is non-degenerate, then the system exhibits a weak field quadratic Stark effect. This is the weak field, and this is also true here. Now, you go to hydrogen n equal to 2. The 2s2p are degenerate, completely degenerate. And you mix them in first order degenerate perturbation theory between the 2s and the 2p, the different components of the 2p. And what immediately comes out is that there is an energy shift which is proportional linearly to the electric field, shown here. There's the blue side and the red side. This is the linear Stark shift. And this is the dipole moment. So hydrogen atom in weak field in equal to 2, because it's degenerate, forms a linear Stark shift. You know this. In molecules, this is how it would work. You would take an s orbital, spherically symmetric, and you sort of mix with it some pz orbital. This is a pz, positive side and a negative side, along the internuclear axis. And then when you mix them up, you get charge separation. There's more positive than negative, and therefore there's a dipole moment, a permanent dipole moment. This is the essence of formation of a permanent dipole moment. This is how it exactly works, for instance, in K or B. So the take-home message from all this is that in order for a permanent dipole moment to form, there has to be some degeneracy involved, or there should at least be nearly degenerate states nearby, which then could be overcome or could be mixed in the electric field and lead to the formation of the dipole moment. So in these homonuclear molecules, which I just described, these Rydberg molecules, the experiment saw a quadratic shift. In other words, the second order shift, or a polarizability, induced dipole moment. An induced dipole moment. We claim that in these same systems, there should actually be a permanent dipole moment. This is counterintuitive because in order to form, I'll go back here, in order to form a permanent dipole moment, you need to break this symmetry between the 2s and the 2p, for instance, in hydrogen. Two nearly degenerate states will have to separate in order to form a dipole moment. So this is what we claim. What we claim should exist in these molecules. And lo and behold, this is the dipole moment, actually, of the permanent dipole moment in these molecules, a function of the principal quantum number. The experiment was done at two principal quantum numbers, here and here, and this is our calculation. I will not go into the scaling of this, how the dipole moment is scaled, because it becomes a little bit involved, but just that, so that you see that these molecules, these Rydberg molecules of rubidium atoms, these are rubidium-2 molecules. They actually form permanent dipole moments. And where they come from is this. They come from is this. So the molecules are made in rubidium equal to 35s state. So it's a rubidium 35 state interacting with the rubidium ground state. However, the moment there's an infinitesimal electric field turned on, even though there's a degenerate manifold which is much farther away in energy, okay, there's no electric field in the system which can actually overcome this splitting in energy. However, because there is this degenerate manifold, this Rydberg degenerate manifold, it mixes in some amount of this degenerate manifold into the Rydberg state, the S state, and from this mixing, this dipole moment forms. So for the first time, we showed that actually a homonuclear molecule can have a permanent dipole moment. In your textbook, analysis or descriptions, it is said that because of the fact that there is a charge symmetry and there is parity symmetry in homonuclear systems, homonuclear molecules made of same atoms, dipole moments cannot form. And I showed you a sort of a derivation of why that cannot happen. But in all of those textbook descriptions, the atoms are in the ground state, electronically in the ground state. But the moment one of the electrons, even though it's a homonuclear system, is excited, and the electron is excited into a Rydberg state, the possibility exists that you can actually break the symmetry, the charge symmetry, as I showed you, and also the parity symmetry. And which in this case does not really matter, and form a dipole moment. Why the exchange symmetry really doesn't matter in this case is because of this. So these are the potential curves for rubidium in the ground state. In other words, going to rubidium 5s and rubidium 5s. There are two of them, right? You know this. There's a grado state, sigma state, and an ungrado sigma state. The so-called exchange symmetry. In a typical molecule in the ground state, the electrons are over here. Therefore, there is a very large splitting between the grado and ungrado states. In these Rydberg molecules, the molecule is actually about a couple of thousand Bohr radii, way out here, somewhere here. And the splitting between these two states, between the U and the G, the ungrado and grado, I do not assume that you should know, but it goes as exponentially with R. So at R, in the order of 1 to 2,000 Bohr radii, this separation is like e to the minus 100. So the delocalization time, in other words, 1 over this, is much, much larger than the age of the universe. In order to be able to tunnel from the grotto to ungrotto and back, it will take much longer than the age of the universe, even if you assume that the universe is about 6,000 years old. It's still a long time. So what happens is that these Rydberg molecules are actually born in charged localized states. So they have a permanent electric dipole moment in the body fixed frame. This is extremely counterintuitive. We take two atoms which are exactly the same, one of them, okay? The electron in one of them is excited to a spherical wave function. Nevertheless, they're exactly the same. But yet, in the body fixed frame, the moment you apply a tiny, tiny, tiny electric field, you give it a direction. That's what the dipole moment means. You have to break the symmetry and give it a direction in this direction, if the electric field is here. And then you go in the lab, you do an experiment, and what you see is a linear shift. And this is the linear shift in the experiment. And these are our calculations. So this would be upstream, downstream, because the electric field would apply to an atom. Electron in an atom would go in two directions. So this is a linear shift. Now, the rotational constant for these Rydberg molecules is about, in these systems, is about 11.5 kilohertz. Just to sort of, to what the rotational constant is. Rotational constant is proportional 1 over reduced mass times the internuclear separation squared. The equilibrium distance between the two atoms in the molecule. And a typical ground state molecule, let's say KRB, the rotational constant is 1 gigahertz. You see this enormous time energy difference or time difference between these two systems. So that a field of, which we have in our calculations or experiment, field of about 9 volts per centimeter for this Rydberg molecule is equivalent to a field of about 10 to the 6 volts per centimeter for a typical ground state molecule. These are, people have done these sort of measurements where they apply a few times 10 to the 6 volts per centimeter to ground state molecules and created these sort of pendular molecules. Pendular molecules are molecules made up of many, many rotational rotational states, which are all superposed into the wave packet, leading to a localized rotational wave packet. This is getting into a little bit of detail, which you probably aren't going to get into. But what I want you to sort of appreciate is that the rotational constant for these Rydberg molecules is extremely small. This again is the manifestation of the fact that the grotto and grotto symmetries are so degenerate. Now, to show this localization, what we did was to take the full wave function for this molecule. This is in rho, the cylindrical coordinate, and z, and then subtract from it the spherical part, the 35s part. So this is the full wave function squared. Shows you the symmetry, okay, or the seemingly symmetric part of the wave function for this molecule, and subtract from it 35s, and then the squared. What is left behind is a dipole moment because the ion is here and the electron is here, and that's the dipole moment. So what I have so far described is between the interaction between the Rydberg atom and a ground state atom. Now I want to make it a little bit more flavorful. Take the Rydberg atom and interact it with another hot particle which we have in atomic physics, polar molecule, an ultracold polar molecule. Let's see what happens. Professor Kern gave you some idea about some of these cold molecules. They're quite in vogue. I know of 3 ways that cold molecules are made, from hot to cold, by running them through buffer gases. So all of these these are some of the molecules, and then there are many more actually, have been formed. You can go from fast to slow. So by stark decelerations, you put up these electric fields, and you constantly switch them over so that you always present barriers to these polar molecules as they move from here to there, so they slow down. Or, which is one you probably are more familiar with, is you go from atoms, which I showed the way we make them, is from atoms to molecules. So you go by large distances, because these are ultracold systems, you absorb a photon, you go to some vibrational levels, you either wait for it to spontaneously decay, or you try to go do something to stimulate it down into ground electronic state. And these are some of the molecules that should be made. And this is, I showed you Rydberg atoms in an optical lattice. This is ultracold molecules in ground state in an optical lattice. This is an experiment of Hans Christoph Negrel in Innsbruck, where they took not polar molecules, but cesium molecules, by melting with EC into a moth in an optical lattice, and then doing these 4-photon styre to get all the molecules into the ground the state of the optical lattice. Now, as I said, I'm going to describe the interaction between a polar molecule now and a Rydberg atom. Previously, I had a ground state atom here. Now I'm going to have a ground state polar molecule. The interaction previously between the atom and the Rydberg electron was the Fermi superpotential. Okay? Short range, very short range, scattering length. However, now the interaction between the electron and the polar molecule, a dipole moment in other words, is like this. It goes as like alpha squared over r squared. And then the dipole moment would have a critical value. Now these units, the actual units that we are familiar with, would be about 1.63 divided. This is known as the Fermi-Teller dipole. So above which, if the dipole moment of the polar molecule is larger than this, than 1.63 divided, it's considered supercritical, meaning that the electron would tend to want to bind itself to this polar molecule and create a negative ion, molecular ion. This has been observed. So the electron would want to go over here and attach itself to this polar molecule, forming a negative molecular ion. But if it is subcritical, in other words, the dipole moment of this polar molecule is less than 1.63 divided, which encompasses many of the ultra-cold molecules that we are familiar with, many of them, not all of them, it's subcritical. And those are the ones that I'm going to concentrate on, so that the electron does not bind. Now, this interaction, it looks isotropic here, but it's actually anisotropic because of the fact that you have charged dipole interaction, and that goes like the first order Legendre polynomial. And I said this is called the Fermi-Teller dipole. And I've taken handwritten notes from the University of Chicago archive of a fairly famous physicist here. Anybody recognizes the handwriting? This Fermi's handwriting, where he derived the so-called Fermi-Teller dipole value. You can see this gamma less than 1/4 is this. So when A is less than 1/4, or is A is, this gamma is my A. You form a critical dipole moment. So the interaction of this electron with this polar molecule would be the kinetic energy, and this interaction, electron-dipole interaction, the sandwich between the different hydrogenic or electronic states. And then there's also, of course, this ion, which would also, because it's a charged particle, interact with this dipole moment. But this interaction is constant. It's 1 over r squared. but just constant. It doesn't change. It's always attractive. Whereas this can be both. Okay. So I didn't grow up working with two-level systems, but I've come to enjoy it recently. Makes life very easy. So the kind of molecules I'm going to describe are two-level systems. Just like this. Up, down, up, down. So they could be lambda doublet molecules like OH, CH. OH is, of course, both, in fact, even CH, are extremely important molecules. I mean, this is when the first maser was discovered in. And also molecules with small rotational constants. KRB, for instance, or rubidium cesium. And represent all of these molecules as essentially two-level systems. In interaction, the molecular Hamiltonian would then look like this. Would be a splitting between them and interaction with some electric field of the dipole moment with the electric field. Now, where does this electric field come from? We're not applying right now any external electric field, but the fact that the electron itself presents to the dipole an electric field. So the Rydberg electron acts to polarize the molecule, give it orientation. So this is the electric field of that of the, this E is charge of the ion, let's say, over R squared, so this is constant. So this is the electric field of the electron with this dipole. This is that of the charge, the ion core is the dipole. So now if you solve for this, okay, then there's a critical dipole value, which then is splitting divided by 2 times this dipole moment, above which then the system polarizes, below which it doesn't. Right? And remember that when we say that the KRB is a polar molecule, or OH is a polar molecule, the molecule itself actually doesn't know that it has a dipole moment, right? When does it know it has a dipole moment? Only when an electric field has overcome this splitting, in other words, has mixed these two states, made a superposition of these two states, that the molecule suddenly says, oh, now I have a dipole. Before that, it doesn't. And this is this value. It's delta over 2D. That's the critical value. So now, if you plot, you solve this, diagonalize the integration. And as a function of R, plot the energy levels. This is given in atomic units, but in the scales that you may be more familiar with, these are in tens of gigahertz. Then you get 2 sets of potentials. Ignore everything that's up here, all these other colors. You just concentrate on this red one and on this black. The red one comes down, it has potential wells, it oscillates. We know what these oscillations are due to the Rydberg nature of the electronic wave function, and it goes up. The other one, the black one, comes down, it does the same thing, and then it collapses. That comes from the fact that you have this term, which is always repulsive. It always actually turns out to be attractive here in the Hamiltonian. And this one, which is due to the electron, can be both attractive and negative. And they play against each other to give you these 2 curves. Turns out, we have shown you this by, you can actually see it by looking at the electronic densities, is that this potential well, the right one, let's call this right and left instead of red and black, right and left. The right one refers to the orientation of the molecule in this direction. This one refers to the orientation of the molecule in that direction. You immediately see that we have now created a system which has a double well. So it acts, because the separations are large, a few hundred Bohr radii, this begins to act like you can actually play around with it, make it Schrödinger cat. Almost a macroscopic Schrödinger cat. Now the critical field, this should be F, is in the order of 500 volts per centimeter in this system. So with 500 volts, you can actually mix these 2 states. Now, these form permanent dipole moments because the ion is here and the polar molecule is here. The electron, you can see that it has been deformed over here and over here, both of them. This one, I think, is over here. This is over here. So this is the electronic wave function for that orientation, and this is the electronic wave function or density for this orientation. Nevertheless, it shows that you get permanent dipole moments. The size of these dipole moments is in the order of 1.3 times n squared. N is the principal quantum number. So, for instance, if you have n equals 35, this Rydberg molecule would have a dipole moment of the order of 2.75 kilodipole. Extremely large dipole moments. And you can do things with it. For instance, you can take it and say by on-resonant coherent Raman, you can Rabi flop between these two states, the left, the right, and the left, right and left, right and left. The reason you can do that is because of this. This potential, the black one is from here, it collapses. This potential collapses eventually. But this red one never does, it actually goes up. So it can support extreme number of vibrational levels, which you can choose to optimize the Frank condoms so that you can go from here to here with very weak pulses with large probability. Coherent. So in other words, you can think of this as having the Rydberg electron ordering this polar molecule to go this orientation or that orientation. This, but this, without doing anything else. Okay? Now, this is a little bit of a chemistry, if you wish. These are the energy levels in OH. So, OH is not a rotational molecule, it's a lambda doublet molecule. What does that mean? That means that in order to make a dipole moment in OH, all you have to do is overcome these two opposite parity states, the F and E states, living in, magnified over here, living in J equal to 3/2 state, in the ground rotational state. In OH, the energy splitting in rotational levels is enormous. It's in the order of 84 wave numbers. It's very large. So even though the molecule does not rotate, it's still a polar molecule. In KRB, I'll show you it's a bit different because these rotational splittings are in the order of 2 gigahertz. So OH has a splitting of about 1.7 gigahertz here and a dipole moment of 1.68. CH has a splitting, same sort of splitting, of 3 gigahertz and a dipole moment of 1.46. Now, we wanted the dipole moments to be less than 1.63, below the Fermi-Teller threshold. So what you can do is butyrate these molecules. In other words, exchange the hydrogen with deuterium, add an extra neutron, and you get splittings to go from OH to OB from 1.7 to 0.5, and the dipole moment slightly decreases from 1.68 to 1.6. And the same thing happens for CH and CP. So these are games that you can play to make molecules you want. And then you can also control them in electric fields. Now this is an external electric field. Okay. External electric field is over here. These are the same molecules. This is the ground molecule, polar molecule, and this is the rubidium Rydberg states. And the Hamiltonian then just becomes the adiabatic Hamiltonian would be that of the molecule, which you just saw, the two-level system, plus this additional term. And then you diagonalize it and all of that. And here's what happens. So I'm not going to get into details of how we do the calculation, but here's what happens. Remember I told you that the quantum defect in alkali systems matters. Professor Kram yesterday, is Roman here? Here. Roman is here, yes. Asked why alkali metals or molecules are so in demand and H2 perhaps is not. And here's the reason why. because of the level of structure that it presents to you, because of the quantum defects. So take, for instance, rubidium N equal 25s. Right? Because the quantum defect of the rubidium in the S state in rubidium is 3.13 over here. Then the energy level of a 28s, okay, you just subtract 28 minus almost 3. What do you get? You get 25. Right? So the energy level of a 28 state is not very far from that of a rubidium N equal 25. This has implications for the electric field behavior of atoms and molecules, alkali metal atoms and molecules, and everything else which follows. So in this case, for instance, what we showed is that these Rydberg molecules, okay, so this would be the equivalent of one of those red curves you saw, equivalent of a black curve you saw. However, now because of the quantum defect, this 28s, you get mixing. The two double wells are presented here, but they're mixed with all of these degenerate manifold states. Which means that now you can actually make these things with two photon photo associations in experiments. How do you do that? You, because of the fact, if you were to make these molecules in fully degenerate states, you need many photons, right, in order to get the higher angular momentum states. However, because of this mixing with the S states, now you can actually do two photon photo association because of the mixing in the normal way that people ordinarily make molecules. And this is showing the mixing. In other words, your wave function would have an admixture of all the degenerate levels, this D stands for degenerate, plus some coefficient mixing from the S manifold. And due to this mixing, you can make these molecules experimentally. And this is to show that you can do the same thing if you have electric field on. So now, these molecules are exotic, they're very interesting. They give you very nice pictures, they get you on the cover of books and things. But are they useful? And it turns out, in some ways, they are. So this is a scheme that we just proposed to be able to extend polar molecule bipolar range through Rydberg excitation. So to sort of walk you through some of the schemes that are available, this is from David DeMille's proposal back in 2002 to create many qubit systems. So you take polar molecules, you apply an inhomogeneous electric field, and then you have these dipoles, polar molecules, these dipole moments. And then what you have to do is that you have to apply many microwave fields in order to flip these dipoles, except for the two which you do not, which you like to create a two qubit gate, and then extend the process. Now, these are typical polar molecules, dipole moments of an order of a divide, so 1 to 10 divide. Another scheme is to sort of create, say, an optical lattice, polar molecules which have a small dipole moments in the order of a divide. But then, put as impurities, you have, let's say, two molecules, let's say metastable, which have large dipole moments, and try to address them. This one was a scheme that was done at ITAMP by Jan and Prabhat and others. Of course, getting these sort of molecules, impurities into the system is going to be itself a challenge. All of these ideas are sort of create many qubit systems and extend range to thousands or 100,000s of qubits through the interaction of so-called dipole-dipole interaction. But most molecules which have in nature, as I said, are of dipole moments in the order of 1 to 10 keV. If you take a typical optical lattice, because the lambda over 2 is in the order of between about 300 to 500 nanometers, about half a micron, then this dipole-dipole interaction would allow you to extend the range to a few lattice cells. And then it dies. So what we thought was this, that we could create very long-range qubits even outside of the blockade region by putting the molecules in an optical lattice and having a nearby gas of atoms, not Rydberg atoms, but just gas of atoms. Let's say in an optical lattice or in a sort of a planar geometry. And then come in with let's say 2 lasers and excite 2 atoms into Rydberg states. And through the interaction of the Rydberg atoms and these polar molecules, as I have just shown you, then I could extend the range of this interaction because these molecules now have dipole moments in the order of permanent dipole moments in the order of kilodivide. Then I can extend this range of interaction between the polar molecules to as large as nearly I want. I'm going to be limited by how fast the gate operation is performed, which should be, of course, less than the decoherence time, whatever decoherence exists in the system. And what eventually limits everything is the lifetime of these Rydberg atoms. The usual decoherence in rotational levels is about 1 millisecond. So if you encode your qubit into rotational levels, you would expect millisecond time scales. If you encode them into hyperfine, then the time scale increases because it's more immune from decoherence. You get about a second or so. But eventually, in these systems, you're sort of limited by the lifetime of the Rydberg. This is what I have here in case you're interested. You'll see either the video or the view graphs. It's just a usual Rydberg blockaded phase gate, which I'm not going to go through. So, I should say set the interaction time scale. So the Rydberg atoms have finite lifetime. Your lifetime is in the order of 10 to 500 microseconds. If the gates are operating at about a microsecond, meaning that your Rabi, either for pi pulse or 2 pi pulse, is in the order of 100 kilohertz, which is doable easily. Then for Rydberg atoms which are interacting by a van der Waals interaction, C6 over R6, then the blockade radius for, let's say, n equals 50 is about 5 microns. So as long as these things are separated, let's say, by more than 5 microns would be fine. For Rydberg atoms which are interacting by a dipole-dipole, then the Rydberg blockade radius is about, for n equals 50, is about 40 microns. Therefore, we can take these systems to be outside of the